Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So for millennia, we've basically looked up at the night sky, at the stars, and we've just assumed that the black space between them was this empty, pristine void.
Right. Yeah, like a vacuum.
Exactly. Just a totally clear glass window to the universe. But it isn't. It is actually this turbulent, completely invisible ocean of warped glass. And for the very first time, astronomers have finally caught it, actively distorting the shape of the universe.
It really forces a complete paradigm shift, I think, in how we perceive the whole galactic environment because, we're so conditioned by popular culture and basic science diagrams to think of space as a perfect vacuum.
Yeah, just a frictionless stage where planets and stars just kind of exist.
Exactly. But in reality, the interstellar medium, or the ISM, is a highly complex, multi-phase environment. It has currents, it has weather, basically. And crucially, it has these massive variations in density.
And those density variations are really the key to this whole revelation. Because when we talk about the interstellar medium, I think people usually just picture gas and dust. But the specific component that's warping our view of the universe isn't just, cold, dead dust floating around.
Yeah, not at all.
It's the warm ionized medium. We were talking about these vast clouds of plasma where the gas has been energized to the point that electrons are just violently stripped away from their atomic nuclei.
And those free electrons, they are the active agents of distortion here. Because when electromagnetic radiation, specifically radio waves in this case, when that travels through a pure vacuum, it moves at the absolute speed of light, totally unimpeded.
Unbothered by anything.
Right. But when that same radio wave hits a region of space that's just filled with these free electrons, the oscillating electric field of the radio wave actually physically interacts with those electrons.
It forces them to vibrate, right?
Yes, exactly. It causes them to vibrate. And that interaction momentarily absorbs and then re-emits the photon, which effectively slows down the phase velocity of the wave.
So it's dragging on the light, essentially. And because this plasma is turbulent, it's not just like one uniform flat sheet of electrons. You have these highly localized pockets where the electron density is incredibly high, sitting right next to pockets where the density is, relatively low.
Right, it's very chaotic.
So as this wide wavefront of radio light comes just crashing through this medium, the parts of the wave hitting the dense pockets get slowed down way more than the parts hitting the less dense pockets.
Which means the wavefront itself physically bends. In optics, we call this refraction. So the turbulent plasma literally possesses this fluctuating refractive index.
I like to think about the chaotic eddies in a hurricane. You have these massive overarching wind currents that clash and then they break down into smaller and smaller swirling vortices.
Until they eventually dissipate as heat, yeah.
Exactly. And that exact same kinetic energy cascade is happening in the plasma between the stars. I mean, the energy from a supernova explosion or intense stellar winds from massive young stars, it injects all this chaos into the ISM.
On the scale of parsecs, which is just massive.
Right. And then that turbulence just cascades down into smaller and smaller density ripples. So when radio light from some distant object passes through this, it gets bent and refracted by every single one of those swirling, invisible eddies. It's essentially a cosmic heat haze.
That's a really great way to put it, actually. The physics underlying your heat haze analogy are identical to what's happening here. It's just governed by plasma dynamics instead of the thermal expansion of Earth's atmosphere.
Right, because in a terrestrial heat haze, you have, asphalt baking in the hot sun.
Yeah, which creates this steep temperature gradient in the air directly above it. And hot air is less dense than cold air, so it has a lower refractive index.
So as light from, say, a car in the distance travels through those swirling pockets of hot and cold air, the light gets messed up.
The phase of the light gets corrupted, exactly. The image arrives at your eye shimmering, spatially shifted. In the ISM, we're just substituting thermal air currents with magneto-hydrodynamic turbulence.
And substituting visible light with radio waves.
Precisely.
But wait, let me push back on this for a second. If the glass has always been warped, and we've known about plasma scattering for, decades?
Yeah.
I mean, pulsar astronomers deal with dispersion measure and scattering delays literally all the time.
They do, yeah. It's a known nuisance.
So why are we treating this specific detection of structure as such a massive first? What's the difference between simply inferring that a scattering disk exists, which we've always done, and what Alexander Plavin's team actually managed to map here?
Well, inferring a scattering disk is really just a statistical assumption. For decades, radio astronomers would look at a compact point source, like a quasar, and they'd notice that at lower frequencies, the object appeared bloated.
It looked artificially enlarged.
Right, like a smeared blob on the image. And the mathematics used to correct for this relied on what we called the thin screen approximation.
Okay, what does that mean?
Basically, we assumed that turbulence acted as a uniform Gaussian scattering screen. It was treated as random, unresolvable noise that simply diffused the light symmetrically in all directions.
Like frosted glass.
Exactly like frosted glass. But Plavin's team didn't just measure a smeared blob. They directly detected and mapped the discrete, asymmetric patchy lenses right within that turbulence.
Oh, wow. So they resolved the actual internal structure of the warps in the glass itself.
Yes. They didn't just say, oh, the glass is blurry. They mapped the individual curves, making it blurry.
That is wild. But to study a warped piece of glass with that level of extreme precision, you can't just use any light source. You need an incredibly bright, very specific kind of optical probe shining through it from the other side.
You need a cosmic lighthouse.
Exactly. And for this specific map, the astronomers utilized a quasar known as TXS 2005 plus 403.
Which is a truly extreme astrophysical laboratory in its own right. It's an active galactic nucleus powered by a supermassive black hole.
But what makes it the perfect probe for this experiment isn't just that it's bright, it's its specific emission mechanism, right?
Right. As material spirals into the accretion disk of this supermassive black hole, magnetic fields funnel a portion of that plasma into twin relativistic jets.
And these jets are shooting outward at a significant fraction of the speed of light.
Yes, and they're blasting out synchrotron radiation.
Right, because electrons are spiraling around these incredibly strong magnetic fields, emitting this brilliant continuous spectrum of radio waves.
And crucially, this specific quasar is located roughly 10 billion light years away.
10 billion, which is a number that's hard to even wrap your head around. But the scale of that journey fundamentally changes how the light behaves by the time it actually reaches us here on Earth.
It does, because when that radio light first leaves the quasar, it's a highly curved, rapidly expanding sphere of energy.
Right, like ripples in a pond moving outward from a single point. But as it travels across 10 billion light years of intergalactic space, just expanding continuously, the curvature of that spherical wave flattens out.
Completely. By the time it reaches the outer edge of our Milky Way galaxy, that incoming wavefront is effectively perfectly flat and planar.
And a perfectly flat planar wavefront is exactly what you need if you want to accurately measure the refractive index of a local screen.
Exactly. If the wavefront was highly curved when it hit the Milky Way, it would introduce all these geometric complexities that would make isolating the local turbulence incredibly difficult, if not impossible.
Because you wouldn't know if the curve was from the source or from the turbulence. So it travels through the absolute near-perfect vacuum of intergalactic space for 10 billion years, totally undisturbed.
Right.
But then, the most critical phase of its entire existence is the absolute final fraction of a second of its journey. Just as it reaches our cosmic backyard, it has to pass through the constellation Cygnus.
And the Cygnus region is, without a doubt, one of the most violent, complex environments in the entire Milky Way.
Why is it so chaotic there?
Because we're essentially looking straight down the local spiral arm of our galaxy, directly into what is known as the Cygnus X complex. It's a massive star-forming region containing dozens of OB associations.
And for the listener, OB associations are clusters of extremely massive, incredibly hot, very short-lived stars.
Right. And those massive stars are blowing out these ferocious stellar winds. And then inevitably, because they live such short lives, they detonate as supernovae.
So all of that explosive kinetic energy is just being violently injected into the surrounding gas.
Constantly. It creates this superbubble of intensely hot, ionized plasma that is just expanding and shredding the surrounding medium. The turbulence in the Cygnus region is orders of magnitude higher than the average interstellar medium.
Wow. So this flat, pristine wavefront of radio light from the quasar, after 10 billion years of peace, just suddenly slams into a chaotic, violently churning wall of electrons.
Exactly. And the phase of the wavefront gets instantly corrupted. Parts of the wave are accelerated, parts are delayed, and the flat plane is just shattered into this complex, corrugated shape.
But to actually measure that corrugation from Earth, you can't just point a standard radio dish at the sky and see that, right? The resolution required to see those tiny phase shifts must be staggering.
It is. Which brings us to the instrumental marvel that made this whole discovery possible in the first place, the Very Long Baseline Array, or the VLBA.
Operated by the U.S. National Science Foundation. And this is where the engineering of radio astronomy just sounds like pure magic to me.
It really does, because the VLBA is not a single telescope.
Right. It's this continent-spanning network of 10 separate 25-meter radio antennas. You have one sitting on the slopes of Mauna Kea in Hawaii. You have another all the way in the Virgin Islands, and then 8 more spread out across the continental United States.
And they utilize a technique called Very Long Baseline Interferometry, or VLBI. You know, in optical astronomy, the resolution of your telescope, like how sharp an image it can actually produce, is dictated by the physical diameter of the mirror.
Right. Bigger mirror, sharper image.
Exactly. But in radio astronomy, the wavelengths we're looking at are so large that to get comparable resolution to an optical telescope, you would need a satellite dish literally the size of a continent.
Which is mechanically impossible to build.
Right. So interferometry allows us to synthesize a telescope of that size computationally.
Okay, so by recording the exact same radio signal from the quasar at all 10 of these distant telescopes simultaneously, you are effectively using the Earth's rotation to sweep out the aperture of a virtual telescope that is over 5,000 miles across.
It's brilliant, but the precision required to actually correlate those signals is where it becomes this monumental physics challenge. You cannot simply combine the data streams casually.
Right, because to reconstruct the wavefront, you have to know precisely when every single crest and trough of that radio wave hit each specific antenna, down to the picosecond?
Down to the picosecond, yes. Which means standard clocks are completely useless.
So what do they use?
Every single one of those 10 telescopes is equipped with its own hydrogen maser atomic clock.
Oh, wow.
These clocks are so stable that they lose roughly 1 second every few million years.
That is insane.
It is. So they timestamp the incoming radio waves as they are recorded onto massive physical hard drives at each of the 10 sites.
And then, because you can't just send that amount of data over the internet, those hard drives are physically shipped, like by mail, to a central supercomputer called a correlator in Socorro, New Mexico.
Yes. And the correlator is what aligns the data streams from all 10 telescopes by matching those atomic clock timestamps.
And it has to compensate for so many variables, right? Like the curvature of the Earth, the minute tectonic shifts of the continents.
Even the extra distance the wavefront had to travel to reach Hawaii compared to the Virgin Islands. It's incredibly complex mathematically, but through Fourier transforms, the correlator reconstructs the interference pattern of the wavefront,
allowing us to essentially see the quasar with a resolution hundreds of times sharper than even the Hubble Space Telescope.
Exactly.
Okay, but let me challenge the methodology here for a second. Because if Plavin's team is relying on analyzing nearly a decade of archival VLBA data, how do they know this patchy distortion they claim to have found isn't just a hardware glitch in the array itself?
That's a very valid question.
Right, because you have 10 dishes operating in completely different climates. They're looking through completely different atmospheric weather systems. They're synced by physical hard drives being mailed across the country. How do you separate an Earth-bound instrument error, or like an atmospheric calibration artifact, from a legitimate interstellar phenomenon happening thousands of light years away?
You have to analyze the properties of the signal across multiple dimensions, specifically frequency, time, and baseline length.
Okay, break that down for me.
So if this were a calibration error, or say a glitch in the Socorro correlator itself, the artifacts would appear symmetrically across the entire synthesized aperture. Or they would manifest as random, uncorrelated phase noise that just doesn't follow the mathematical laws of optics.
Okay, what about Earth weather?
If it were an atmospheric error, say a severe thunderstorm passing over the telescope in Pie Town, New Mexico, the phase distortion in the data would change on a timescale of seconds or maybe minutes because Earth's weather moves incredibly quickly relative to the size of the telescope.
Right. But interstellar weather moves on a cosmic timescale.
Exactly. The patchy distortions that Plavin's team found were persistent. They remained relatively stable over months and even years of archival observations. An atmospheric error simply cannot persist in the exact same configuration over a single telescope for 5 years.
That makes perfect sense. But what about the quasar itself? I mean, active galactic nuclei are constantly flaring. They're changing their jet structures, spitting out new blobs of plasma. How do we know the patchy structure isn't just the quasar physically changing its own shape over time?
We know it's not the quasar because of how the scattering behaves across different radio frequencies. Synchrotron radiation from a quasar jet has a very specific intrinsic spectrum, but plasma scattering is highly dispersive.
Meaning what exactly?
It means the refractive index of plasma is deeply dependent on the wavelength of the light passing through it. Specifically, the scattering angle scales with the square of the wavelength.
Okay. Meaning lower frequencies, which have longer wavelengths, get bent and scattered dramatically more than higher frequencies.
Yes. So if the patchy structure was intrinsic to the quasar itself, it would look relatively similar across adjacent frequency bands.
Because the object itself looks like that.
Right. But the structural changes the team observed scaled mathematically in exact accordance with the plasma dispersion laws. The fingerprint of the distortion proved definitively that the signal was being warped by a local intervening screen of ionized gas in the Cygnus region, not by the quasar itself.
Wow. Okay, so once they confirmed the signal was genuinely interstellar, the results completely shattered the prevailing models of how the scattering is supposed to work, didn't they?
Totally shattered them. The classical expectation, that thin screen approximation we discussed earlier, predicted a very specific outcome when looking at Quasar TXS 2005 plus 403.
Right, because under the classical model, the intensely turbulent Cygnus region should have acted like a dense sheet of frosted glass.
Exactly. As the flat wavefront from the quasar hit the screen, the random microscopic density fluctuations in the plasma should have scattered the radio waves uniformly in all directions.
And the result should have been a smooth Gaussian blur. The point-like quasar should have been mathematically smeared out into this diffuse glowing orb.
And that leads to a very specific prediction regarding the VLBA itself. In interferometry, the physical distance between any two telescopes is called a baseline.
Okay.
Short baselines, like the distance between two antennas in the American Southwest, they are great at capturing large, diffuse, blurred structures in space. But the longest baselines, say the distance between Hawaii and the Virgin Islands, are only sensitive to highly compact, intensely sharp point sources.
So if you point the longest baseline at a diffuse, smooth blur, the signal washes out entirely. The wavefront is too disorganized for those two distant telescopes to find a correlating phase.
Precisely. Based on the density of the Cygnus region, standard scattering theory dictated that the quasar signal should have been completely pulverized. The blur should have been so diffuse that the most distant pairs of telescopes in the VLBA network should have registered absolutely zero correlation.
They should have been mathematically blind to the quasar.
Completely blind.
But they weren't. When Plavin's team processed the data, those distant baseline pairs clearly detected a signal. They picked up this faint, highly structured glow that absolutely should not have been there under the old models.
Right. They didn't find a uniform blur. They found structured, asymmetric, patchy distortions. The scattered light was highly organized into discrete subimages.
And this is where I'm a bit hung up on the optics of this. Because if you have a wildly turbulent, chaotic plasma screen where the refractive index is just fluctuating violently,
Right.
Standard physics says that chaos diffuses light. It drops the surface brightness.
Generally, yes.
So how does a totally random, messy cloud of gas accidentally coordinate itself to focus light like a coherent lens, preserving enough phase structure for a baseline 5,000 miles across to actually detect it?
It's a great question, and it comes down to the difference between diffractive scattering and refractive scattering.
Okay.
The frosted glass blurring effect we keep mentioning, that's caused by diffractive scattering, very small-scale ripples in the plasma that scatter light uniformly. But turbulence exists on a spectrum of scales.
Oh. Right, the hurricane analogy.
Exactly. So alongside those microscopic ripples, you have much larger localized gradients in the electron density.
The larger eddies in that kinetic cascade.
Yes. When a region of plasma has a density gradient that happens to be shaped like a concave or convex curve relative to the incoming wavefront, it acts as a macroscopic lens.
Just naturally.
Right. And because the refractive index of plasma is less than 1, a region of lower electron density acts like a converging lens, while a region of higher density acts like a diverging lens.
Okay, so within this turbulent screen, you literally have thousands of these temporary, erratic, low-density pockets acting as massive converging lenses.
And just like a normal glass lens focuses sunlight into a sharp, bright point, these plasma lenses bend the quasar's radio waves into overlapping focal paths. And where those paths intersect down here at the Earth, they create a phenomenon known as caustics.
Caustics. Okay, caustics are those bright, undulating webs of light you see at the bottom of a swimming pool on a sunny day, right?
That's the perfect analogy, yes. The water surface is undulating, it's acting as a dynamic moving lens, and it focuses the sunlight into sharp, bright lines on the pool floor.
So that exact mechanism is happening in space. The Milky Way's turbulent ISM is creating a caustic network of radiolite across our entire solar system.
Yes. The VLBA wasn't looking at the main, unscattered image of the quasar. It was picking up the intense, highly focused subimages created by these exact caustics.
Oh, wow.
The erratic lenses were inadvertently grabbing the scattered light and focusing it directly at those distant telescope pairs, magnifying the signal far beyond what the smooth blur models predicted.
So they basically captured the physical geometry of the turbulence itself.
Mm-hmm.
We mapped the specific solar system-sized eddies within a plasma cloud thousands of light years away.
We did. And the sheer scale of that is difficult to process. These lenses, these low-density pockets bending the light, they are billions of miles across.
And the physical scale of this discovery is really why the whole astronomical community is paying such close attention to this, right? Resolving the structure of the interstellar medium down to the scale of astronomical units, which is the distance between the Earth and the Sun, provides this missing link in our understanding of galactic fluid dynamics.
It's a huge missing link.
We mentioned the kinetic energy cascade earlier, the idea of supernova energy breaking down into smaller and smaller eddies. Why is mapping the bottom end of that cascade, the solar system-sized lenses, so absolutely critical to astrophysics?
Because that dissipation scale dictates how the galaxy regulates its own temperature and structure.
How so?
If turbulence dissipates energy too quickly, the gas in a giant molecular cloud cools down and collapses under its own gravity incredibly fast. And that leads to a massive, uncontrollable burst of star formation.
Which sounds cool, but the galaxy would basically burn through all of its gas reserves and just die out prematurely.
Exactly. It would burn bright and fade fast. But if the magnetic fields within the plasma sustain the turbulence down to these extremely small scales, that kinetic energy acts as a pressure support.
Oh, so it's pushing outward.
Yes, it physically holds the gas clouds up against the crush of gravity, which regulates the pace of star formation. By mapping the exact shape, density, and persistence of these AU-scale plasma lenses, theorists can finally calibrate their magnetohydrodynamic simulations.
So we can observe exactly how the turbulence supports the gas right before the threshold of stellar birth.
Exactly.
And there is a direct, tangible application of this map that extends even beyond star formation. It connects to arguably the single most difficult observational challenge in modern astronomy right now, which is capturing a clear image of Sagittarius A, the supermassive black hole at the center of the Milky Way.
Oh, absolutely. The Event Horizon Telescope collaboration achieved a monumental milestone a few years back by releasing the first image of Sagittarius A.
Right, the glowing orange ring of accreted plasma surrounding the dark shadow of the event horizon. But the image is notoriously blurry.
Very blurry.
And the EHT is an interferometer just like the VLBA, but it operates at much higher frequencies, right?
Yeah.
It synthesizes an Earth-sized telescope using observatories from the South Pole all the way up to Greenland. So if they have an Earth-sized aperture, why does the black hole look like a smeared donut?
Because of the exact same phenomenon Plavin's team just mapped. To look at the center of our galaxy, the EHT has to peer through the entire galactic plane.
Right, we're inside the disk trying to look at the center of the disk.
Yes. So we are separated from Sagittarius A by 26,000 light years of the thickest, most intensely turbulent interstellar medium in the entire Milky Way.
The scattering screen between us and the galactic center is just devastatingly strong.
It is. And we established earlier that the scattering angle scales with the square of the wavelength. This is entirely why the EHT observes at the incredibly high frequency of 230 gigahertz, or a wavelength of 1.3 millimeters.
Because if they attempted to image the black hole at lower frequencies, like the standard centimeter wavelengths used by the VLBA, what would happen?
The lambda squared scaling means the diffractive blurring would be so utterly severe that the black hole's event horizon would be entirely washed out. You wouldn't see a ring at all.
Wow. But even at 1.3 millimeters, the image of Sagittarius A is still severely degraded by refractive scattering. The donut shape we see is the intrinsic structure of the accretion disk, but its thickness, its exact asymmetric brightness, the precise shape of the central shadow, all of that is distorted by the chaotic plasma lenses sitting in the galactic plane.
It is the ultimate frustration for astrophysicists. We have built an instrument capable of testing Einstein's theory of general relativity in the most extreme gravitational environment in the galaxy, but we're basically being forced to look at it through the bottom of a violently churning swimming pool.
That is precisely why Plavin's discovery is revolutionary. Because until now, The EHT teams have had to rely on probabilistic modeling to try and guess the properties of the scattering screen. They try to computationally subtract just a generic blur.
Right. But if we can map the discrete patchy lenses, if we can track the exact physical structure of the refractive caustics, we transition from guessing to deterministic correction.
We can map the specific ripples in the pool.
Yes. By studying how these plasma lenses behave over time, how they shift, and how they bend light at different frequencies, astronomers are developing algorithms to completely characterize the scattering screen in front of the galactic center.
We are essentially designing the ultimate dynamic pair of prescription glasses for the Event Horizon Telescope. If we know the exact optical prescription of the interstellar lenses, we can run the interferometry data backward through a deconvolution algorithm and just mathematically strip the turbulence away.
The implications for physics there are just profound. A sharpened, unrippled view of the Sagittarius A, a photon ring, would allow us to measure the spin of the black hole with unprecedented accuracy.
We could observe the exact dynamics of magnetic reconnection in the accretion flow.
Exactly, and vigorously test for deviations from the Kerr metric of general relativity.
But to achieve that level of mastery over the scattering screen, we can't just rely solely on historical archives, right? The astrophysics community recognizes the urgency of this, which is why the team is not stopping with just this initial detection.
No, the National Science Foundation has approved a massive, dedicated follow-up observing campaign using the VLBA, which is scheduled to run continuously through 2026.
And the methodology of this new campaign really highlights a critical feature of the ISM, which is that we are not dealing with a static painting here. We are tracking a highly dynamic, actively shifting vector field.
Everything is in orbital motion constantly. The Earth is moving at 30 kilometers per second around the sun.
And the solar system is orbiting the galactic center at roughly 230 kilometers per second.
Right. And the plasma screen itself in the Cygnus region has its own transverse velocity relative to our line of sight.
Because of that combined relative motion, the specific alignment of those plasma lenses, the caustic network sweeping across the Earth, it's constantly shifting.
It's like driving a car through a moving heat haze. The distortion pattern evolves over time.
Pulsar astronomers refer to this as dynamic scintillation, right? As the Earth moves through the caustic network, the interference patterns create these peaks and troughs in the radio intensity.
Yes, so by continuously monitoring Quasar TXS 2005 plus 403 through 2026, the VLBA will track the precise transverse velocity of the turbulent screen.
They will literally watch the plasma eddies drift across the line of sight in real time. They're gathering enough phase data to build a four-dimensional predictive model of the interstellar fluid dynamics.
We will transition from having just a single topographical map of the turbulence to a full hydrodynamic weather forecast of the interstellar medium.
That is unbelievable.
We will be able to predict exactly how the phase of an incoming wavefront will be corrupted based on the proper motion of the plasma lenses.
It totally redefines the purpose of these instruments. I mean, think about it. Right now, 10 massive radio dishes stretching from the volcanic peaks of Hawaii to the Caribbean Sea are staring intensely into the constellation Cygnus. And they're not actually looking at an object. They are analyzing the empty space in between. They're mapping the invisible architecture of the void.
It really is the ultimate testament to the evolution of observational astronomy. Historically, the intervening gas was just treated as a nuisance, just a layer of contamination that had to be filtered out to do the real astrophysics.
But the contamination contains the fundamental secrets of galactic evolution. The exact same turbulence that frustrates black hole astronomers is the physical mechanism that dictates the dissipation of supernova energy. It is the kinetic structure that regulates the gravitational collapse of molecular clouds.
Right, the obstacle is the actual thermodynamic engine of the galaxy. By analyzing the distortion, we gain access to the fluid mechanics of the cosmos on a scale that just simply cannot be replicated in any terrestrial laboratory.
We started this journey looking at a flat, pristine wave of energy born from the relativistic jet of a supermassive black hole 10 billion years ago. It traversed the entire intergalactic void through the vast majority of cosmic history, entirely unbothered.
Just coasting.
But its actual scientific value was unlocked in the very final fraction of a second, when it violently collided with the chaotic, turbulent plasma of our own local neighborhood. So the next time you step outside on a deeply dark night and look up at the stars, force yourself to look at the blackness between them. It is not an empty vacuum. It is a dense, churning ocean of magnetic fields and ionized gas, actively bending, focusing, and shaping the light of the distant universe before it ever reaches your eyes.